Hey class, welcome to week two's discussion. In this week, you were asked to think of a linear function as well as a quadratic function and give the domain and range of both. And then for the quadratic function, give the optimal value. So I figured I would concentrate primarily on the second part of that, which is the quadratic function, because over the years I've noticed that this is where some people get hung up. So I figured I'd give you an example before you start so you can see what the difference is between what you may have assumed we wanted and what we actually do want. Okay? So I won't talk much about linear functions, except I will say this one thing. If you think of a linear equation as y is equal to mx plus b, then the function just says that y is a function of x. So if we were to rewrite this, f of x as equal to mx plus b, you've now changed the linear equation to a linear function. Everything else stays the same. So when you're looking for the domain of a linear equation or a linear function, it's all the x's that make sense. So if I have, for example, a fraction and I have the x in the denominator, clearly where that denominator becomes 0, that's not a possible value because you can't divide by 0. So that would not be included in the domain. However, for all the lines, if you create just a regular line like mx plus b, then the domain is usually all real numbers. Okay? The key there is the context. So if you remember week 1, there are some numbers or a set of numbers where it doesn't make sense in the business context, in which case the domain would change where it only makes sense. So even though mathematically I can get an x is equal to negative 5, to represent I have to have negative 5 people, logically you can't have less than 0. So rather than have all real numbers, in that case, I would have a lower limit at 0. Okay? And the range is just simply where the y value exists for the domain. So if I have all real numbers for the domain, I probably have all real numbers for the range. But when I have a bounded domain, the range, and it's a linear function, the range is going to be the value at the bounds. So if I have y is equal to x prime, x and x prime is my boundaries, then if I find the value of f of x and f of x prime, these are generally my range boundaries. Okay? So that's about all I want to say about the linear part. I want to focus this particular video on the quadratic part. So let's get to it. So if you notice, I have an example of a quadratic function. Okay, it may not look like that because I don't have an ax squared plus bx plus c is equal to 0. But by subtracting y from the right side and subtracting 15 from the right side and then setting it equal to 0, you can see it in a function or a format that you're probably most familiar with. Okay? So at this point, what most of you guys typically do is solve it. Okay? And you can factor this. You notice I have a 2y here. So you'd have, all right, I want 2y and y would probably be my start. Then I have 15 here. I think, okay, 15 and 1 are 5 and 3. You just plug and see which one makes sense. 5 and 3 makes sense because 5 and then 3 times 2 is 6. So 6 minus 5 is negative 1. So, okay, if I use these two terms, when I multiply them together, I get 2y squared minus y minus 15 is equal to 0. So I factored it okay. And then if I know if anything times anything is 0, then either the first thing is 0, the second thing is 0, or they're both 0. So I can split my two factors into 2y plus 5 is 0, y minus 3 is 0, and then solve for y in this case, which is negative 5 halves for the first factor, and 3 for the second factor. Two notes here. Number one, we're using y as just a variable in this case. But because y is the independent variable, we're really talking about an x. Okay, so the y that you would think of is probably the 0. Okay, so I can replace y with p, k, j, x, t, z. They're all just a variable name, but they represent the x value or the independent value. So what this is saying is I have a value of my x coordinate of -5/2 and a value of 3. And you would go on and you say, okay, here's my solution to the particular discussion. But I want to go back and explain to you, these values are not the optimal value for the quadratic equation. They are the roots of the quadratic equation or the solution to the quadratic equation, but they're not the actual permanent optimal value. Okay? So optimal means the maximum or the minimum. Okay, so if I had a parabola that looks like this, like a bowl, then the lowest number, which is a minimum, this point here is your optimal value. Okay, what we've calculated are the points where it crosses the x-axis. So this point and this point are what we've calculated here. Okay. But you know you can have a value that's greater than it. You can have a value that's less than it. So these are not optimal. Okay. So do not confuse solution or root with optimal value. So now since you know that, let's find a way to actually calculate the optimal value, which is what we want. So when you have an equation, as in the ax squared plus bx plus c equals 0 format, it's relatively simple to find the optimal value. The first thing you have to do is find out what a, b, and c represents in your case. So for us, the value in front of the quadratic term is your a, which is 2. The value in front of your linear term, which is the y, you'll see is b is -1. And then the value in front of your constant is your constant c, which is -15. So in our case, we have an a value of 2, a b value of -1, a c value of -15. Next thing you want to do is concentrate on this term right here, -b/2a. If you find the value of -b/2a, and I'm calling it x here because it's an independent value, but x really does represent this y here. Okay? So don't get confused there. But if I plug in the values of b and a into this equation, I get -1, which is the positive 1, over 2 times 2, which is 4, which is 1/4. So this says that x is equal to 1/4. This gives me the location of my optimal value. But to find the value of the optimal value, I have to solve the equation at that location. So you'll notice I have a 1/4 here. You need to take that value and plug it back into your actual equation. Okay? I plug it here and plug it here. And we've done that as well. Okay? So you have to 2 times 1/4 squared, which is 1/16, minus 1/4 minus 15. And a little bit of math. 1/4 squared is 1/16 times 2 is 2/16, which is 1/8, minus, okay, I said a little bit of math as I screw up a little bit of math. 1/4 is the same as 2/8, so it's minus 2/8, minus 15. So this is -121/8, or you can think of this, as you probably do, as -15 and 1/8. Okay? So my optimal value is located at 1/4, comma, -15 and 1/8. I want you to keep that in mind as we move forward. Okay, so for those of you who are familiar with calculus, you can think of this as a derivative. Remember, the derivative gives you the max and minimum. So if I took the derivative with respect to y in this case, of this term here, you remember you bring down the exponent, multiply it by whatever coefficient's front, the actual variable, and then 1 minus the exponent. 2 times 2 is 4. 2 minus 1 is 1. 4y. Okay? So this first term would have given us a 4y. The second term, a constant times the derivative times the variable. The derivative of that is just a constant, which is where the -1 comes from. And the derivative of a constant is 0. And you set this to 0, so you have 4y minus 1 is 0. Solve it for the variable, you get y is equal to 1/4, which is the exact same value we got the second way. For those who are unfamiliar with calculus, don't worry, this is not part of your class. You can actually ignore this slide if you want to. But what I wanted to show you is once you find out the location, you can then plug it in and find out what your value is. Okay, so a little bit about the graph of a quadratic function. Okay? Remember we had 2x squared minus 2y squared minus x minus y minus 15. Okay? And we had an a of -2. Okay? If your a is positive, then you're going to have a bowl or parabola that's facing up. And your optimal value is going to be a minimum. If, on the other hand, your a is negative, like if we had this to be -2x squared minus y minus 15, your graph is going to be a bowl facing down or a downward facing parabola. And in this case, your optimal value is a maximum. So just remember, when a is positive, you have a regular parabola with a minimum. When a is negative, you have an upside down parabola with a maximum. Now, here's the last clue I'll give you before I let you go. If you think in terms of the solution to an equation, I'll just give you another page here. If you think in terms of the solution to the equation ax squared minus bx minus c, okay? And if you calculated b squared minus 4ac, okay, then this term will help you determine whether or not you have one solution, two solutions, or no solutions. Okay? So if this term is positive, I have two solutions. Okay? If it's equal to 0, I have one solution. And if it's less than 0, there are no solutions. Okay? So those of you who are more familiar with the math from high school may notice that this term here looks kind of familiar. And it might look familiar because of this reason here. It is actually the inside part of the square root term of the quadratic equation. Yep, it's back. Remember, negative b plus or minus the square root of b squared minus 4ac over 2a? Remember that thing? Well, the b squared minus 4ac is under the radical. And we know that if we're not talking about imaginary numbers, I can't have a negative square root. So if it's less than 0, I can't have the square root of 0. Well, that just falls out, right? So if I had 0 under there, the square root of 0 is 0, and then negative b plus or minus 0 over 2a. Negative b plus 0 and negative b minus 0 is the same thing. It's just negative b. That goes away. And so I have one answer, negative b over 2a. But if it's negative, I can't take the square root of a negative number. So I have no solutions. And if it's positive, I'll have two solutions because whatever the value is, I'm adding it and I'm subtracting it. Okay, I think that's about it for me. Oh, yeah, by the way, on the other one, the domain of the quadratic function, okay, is probably all real numbers, assuming it ranges from negative infinity to positive infinity. But there are times when the graph will not actually touch when the graph won't actually touch either of the axis. Like, for example, I'll give you one more example here. If I have a graph like this, for instance, okay, this is a quadratic equation. It will, in fact, have a minimum because it's facing upward. But you'll notice it doesn't touch the x-axis. So the minimum value is going to be a boundary of my range for the quadratic equation. So this would range from my minimum to infinity. Okay? Does that make sense? If, on the other hand, it looked something like this, I still have a boundary of minimum to infinity, but in this case, my minimum is going to be negative. Right? If, on the other hand, I had something like this, then my boundary is actually negative infinity to whatever my maximum is, because I can't go past my maximum. And you'll notice that this continues in every direction along my x value. So my domain is going to be all real numbers. All right, that really is it for me. I will talk to you guys later. Have a great day.